Today, we are going to discuss light spectra. A phenomenon that you should be aware of is that if we had to observe a white light source through, say, a prism or a diffraction grating, we should observe a continuous spectrum of colors ranging from violet at around 400 nanometers to red at around 700 nanometers. We are talking here about dispersion of light. Now, let us imagine that we are burning some kind of gas. The color of the flame will vary according to the gas used. For instance, something which you're familiar with, methane will give a bluish flame, just like we get in gas cookers, and so on and so forth for the various gases. Instead of burning the gas, nowadays it is possible to observe the light emitted by a gas using discharge lamps, like the ones I'm showing here. Okay, so these are called discharge lamps, where the particular gas is entrapped at the middle, and via electricity we get the illumination. And as we're saying, the color will depend on the type of gas that there is inside the lamp. Now, what if we had to analyze light obtained from, say, hydrogen? In other words, what kind of spectrum would we obtain if we had to disperse light from a hydrogen flame or a hydrogen lamp? So here we have a hydrogen lamp, and we are getting the color spectrum after light passes through a prism or through a diffraction grating. Light disperses, and this is the result. Unlike the case with white light, which gives a nice continuous color spectrum, we get instead very isolated or discrete color lines, like the ones we have here. With very wide black regions in between, like the one I'm showing here, which show missing or absent colors of light. We call this an emission line spectrum. And you can see that with hydrogen, we just get 4 color lines in the visible region of the electromagnetic spectrum. Now, it is interesting to note that each gas has its own spectrum. And in fact, we find that these emission line spectra are characteristic of that particular gas. As a side note, I have included a picture, which I'm sure reminds you of the summer night sky in Malta, which shows how various colors may be obtained by burning various elements. But of course, this is rather unimportant for today's lesson. Similar to emission line spectra, we could also have absorption line spectra. Absorption spectra are the exact opposite of emission spectra. Let us imagine having a white light source. As we said earlier on, if we had to disperse white light, we would get a nice continuous spectrum of colors. But what if we let the light to pass through hydrogen gas? We would observe a color spectrum with missing color lines, which correspond exactly to the emission line spectrum we would obtain if we had to burn hydrogen or power up a hydrogen discharge lamp. This is very clear in the next figure here, where we can relate each missing color line with a color line in the emission spectrum. And so on. This technique of analyzing absorption spectra is very useful in understanding the various chemical compositions of unknown substances, such as when studying light from distant stars, which allow us to identify which gases are present in their atmosphere. For instance, if we had to analyze carefully the light we receive from the sun, we would find a lot of missing colors due to gases present both in the sun's as well as in Earth's atmosphere. Of course, you don't need to know by heart any of these details. Now, this was an introduction. In the following session, we shall be discussing the theory behind these spectral lines, which will give you an understanding as to why we get emission and absorption line spectra from gases. Bye.